What is a limit? A limit is a means of addressing a situation that comes up sometimes, surprisingly often, in fact, and that is that we need to understand what a function is doing at a point where, in fact, the function is not even defined. So, for example, consider this function. Now, here we're looking at a graph of this function f, and we have this curve, but you note that there is this gap here at the point A. The function is not defined at the point A. So what can we say if we were to need to understand what the function is doing at that point? How would we address that question? Limit is our means of answering that question. Okay, now one point of view that you can take on this is that in representing the fact that this function is not defined at the point A, you'll notice I put this little circle, that little indicating a hole. Well, I had to put that hole at a certain place. That place has a certain value, and one point of view you could take on what is a limit is where the hole is, in a sense. Now this is just for intuition purposes. So another way to make that, another way to say that is, where would you fill in the function and make the resulting curve continuous? Now I have to put an asterisk here. We can't really say continuous, strictly speaking. There are definition issues involving continuity and limits. But for intuition purposes, we have this idea of a continuous curve. And this is a reasonable picture to have in your mind as sort of a starting point of view on continuity. So the limit is the value that you would fill in at the point where the function is not defined to make the resulting curve continuous. Okay. All right, so that value is called the limit, and we use this notation. We say lim to indicate limit. The point that we're approaching, we indicate that as a subscript, and the function of which I'm computing the limit, we put there. Okay. All right. Now let's be a little bit more precise about it. Here's a way to indicate a little bit more precisely what we mean by limit. So if L is the limit of this function f as x approaches a, what we mean is that you can make the function arbitrarily close to this value L. So keep in mind we have this function f, and the assertion is I can ensure that that will be arbitrarily close. However close you need it to be, we can ensure that f will be that close to L. And we ensure that by requiring that x be appropriately close to a. So simply by requiring x to be close to a, we can ensure that f of x will be close to L. Let's see a picture. So here is a curve. And we note that there's this, again, a hole in this graph. This function that I'm describing is not defined at this point A. Okay. And I am asserting in this picture that the value of the limit here is this value L. And now, how could I ensure that the value of the function be this close to L? Well, that close to L means that the value of the function would have to be somewhere in this interval here, because it could be that close either on the above or below side. So can I do that? Can I ensure that the function will be no more than that distance away from L? Well, yes, I can. The way I'll accomplish that is by requiring this function, requiring x to be no more than that far away from A. In other words, requiring that x be somewhere in here. Of course, I can't allow for x to actually equal to A because, as we noted earlier, the function is not defined at A. So, but notice what happens when I require x to be no more than that far away from a, then the value of the function comes from that little piece of curve, those two little pieces of curve, which means that the values of the function are in that range, and as required, it is within the required tolerance, no more than that far away from L. So by requiring that x be sufficiently close to A, we are ensuring that f of x is as close as was required to L. Okay. Now, the pictures that we've drawn here I picked an arbitrary distance there. But I need to know that this is going to be true no matter how close we need to ensure f is to L, no matter how close. And so we have to consider, well, what if instead of requiring that f be that close to L, what if I needed it to be closer? What if I needed it to be, let's say, no more than this far away from L? All right, in other words, what if I needed to ensure that the value of the function was in this range? Well, can I do that by requiring the function be, by requiring x to be appropriately close to A? Is there some restriction that I can put on how far x is away from A? And in fact, there is. You look at this curve and you say, well, look, as long as, I can sort of cheat and draw that little line and that little line, and I see that if I were to require x to be no more than that far away from A, then the value of the function would come from these two little pieces of curve, and therefore the value of the function would be somewhere in either there or there, and as required within the allowed tolerance distance from L. So this is always going to work. You can see that no matter how small of a distance we require, no matter how close these lines get to each other, there's going to be some appropriately small interval around A that I can make that will make this work. Okay. So this is a way of being precise about what we mean by where is that hole? Where is it that I would fill in to make this seemingly continuous? Okay. All right. So now that works for this function. For this function f, the graph is this curve. What if we have a different function? And will this always work? What if I pick a different value of L, for example? Well, we do have to observe that you have to pick the right value. So let's look at the same curve here. Same curve. And suppose I were to try to assert that the limit is equal to this value. So looking at that value, can I ensure that no matter how close I require f to be to L, can I ensure that simply by requiring x to be no more than a certain distance away from A? And no, this is not going to work. So let's observe, for example, if I would try to ensure that the function is no more than this far away from that value L, no matter how tight around A I make that interval, no matter how close I require x to be to A, there are going to be some pieces of this resulting little bit of curve over here that give values of the function that are simply outside of the given tolerance distance away from L. So this simply is not the limit. This value L does not have the required feature. it is not true that I can make the function arbitrarily close to L by requiring x be sufficiently close to a. I cannot make the function arbitrarily close to L because the function keeps wanting to also be up here near, as you will notice, the actual value of the limit. Right, that is, from the previous page, the actual limit. So there's going to be one value at most, certainly for this function, that can be this limit. Sometimes there isn't a limit at all. So let's look at this example. Here's a function. This function is defined for all the values pictured here other than a. The function is not defined at the point a. And is there any place that I could put the limit, that I could put L, that would satisfy the required condition? And no, there really isn't. Let's play the game a few times. Looking at where I drew this little circle here, based on that, let's suspect that maybe that's the limit. Let's put L there and see if the required condition holds. Well, even if I merely need to require f to be no more than this far away from L, I already can't succeed in that. I can't accomplish that simply by requiring x to be close to a. No matter how close I require x to be to a, there will be some values of x, and the value of the function is outside of that tolerance distance from L. So I cannot ensure f of x is within that chosen distance from L simply by requiring x to be no more than that distance away from a. So this is not the limit. Okay, well then maybe we picked the wrong value. Let's consider a different value. What if I tried to show that this value here, I tried to show that that was the limit? Well, then consider this little interval. And no matter how close I allow I require x to be to a, there will be some values over here on the left side that give values of the function outside of the allowed tolerance. Okay. What about we split the difference? What about we pick something halfway in between? And this also doesn't work, because if I want to require f of x to be in this window, no more than that far away from L, there's no way to accomplish this either. No matter how small I make one of these intervals here, there will be plenty of values of x as close as required to a that simply do not give values of f of x that are appropriately close to L. So I appeal to the listener's intuition that there's just nowhere at all that I can put L. None of those values are going to work. There is no limit in this case at all. So this limit, as x approaches a, of this function does not exist. Right. Now, how do we compute these things? Well, there's a lot of different methods that apply in different situations. I'm just going to show one method that applies in this one particular situation, and there's too much to be said to fit in this short video to do more. So let's compute this limit here. I'm considering the limit as x approaches 2. And note that the function that we're trying to compute, that we're trying to understand at x equals 2, this function is not defined when x is equal to 2. Because when you plug in x equals 2 into there, the numerator is 0, and likewise the denominator also 0. So this function is undefined at x equals 2. Now, the function is perfectly well defined away from x equals 2. So over here, the function is fine. No problem. Perfectly well defined over there. And it's perfectly well defined over here when x is greater than 2. But at 2, the function's not defined at all. So how do I get my hands on what the function is doing? How do I understand this function if I'm interested in what's happening at 2? Okay. Well, notice that factors like so. And so this function here, whose limit I'm interested in, there's an opportunity here for a cancellation. We would like to just cancel the x minus 2's. Now, we have to be a little bit careful about that. What if x minus 2 were equal to 0? You're not allowed to cancel 0 over 0. It doesn't make any sense. The good news is x is not allowed to equal to 2. In some sense, the whole reason we're here in the first place, wondering about the value of this limit, is the fact that I cannot plug in x equals 2. So because x is not allowed to equal to 2, it's perfectly fine to cancel that, and therefore this expression that I'm interested in is just x minus 2, and therefore the limit that I'm interested in is the same as that limit of this function x minus 2. So let's draw pictures now of these two functions. X minus 2, well, this is an easy function to draw a picture of. It's a straight line, right? Y equals x minus 2. No problem. This function, I now have a pretty good way to get a handle on what that function looks like. It looks just like x minus 2 as long as x is not equal to 2. So that means this weird function that I'm trying to understand its behavior at x equals 2, it looks exactly the same as this, except at x equals 2. Where x is equal to 2, of course, this function's not defined, and so notice the gap there. Okay. All right, so trying to understand this limit, well, because these functions agree everywhere except for at x equals 2, that limit is equal to this limit. And in the case of this limit, it's not hard to persuade yourself that 0 is the value of that limit.